Science never stops progressing. Things that seemed like science fiction in medicine and technology 20 years ago are now part of our daily lives. However, there are still questions science hasn't answered. For example, how did life begin? What happened before the Big Bang? How can we explain ghost sightings? And many other questions that remain unanswered. Imagine you have a magic box that can grant any wish. You can ask it for an apple, and it will give you an apple. You can ask for a book, and it will give you any book you want. You can even ask for a mythical creature, and it will appear. But here's the thing. The box can't decide on its own. It's you who makes the wish and opens the box. Before you look inside, anything could be in there. Once you choose and open the box, it becomes whatever you wished for. In one moment, all possibilities exist inside the box, and this is what rules the quantum world. In quantum physics, a particle can be anything before it's observed. Once observed, it becomes something specific. One of the best explanations for this is the Copenhagen interpretation. It says that observing a particle causes it to change its nature, its quantum properties, and its position. This is called the quantum wave function collapse. Measuring a particle makes it leave its previous state, known as superposition, and take on a definite position. Theoretically, opening the box and looking inside is like observing a particle and causing it to change to a specific state, meaning you get whatever you think of. Everything we call reality is made up of things that can't really be considered the real world. Ancient scientists believed the universe was made of air, fire, and water. They used these three elements to describe the entire cosmos. Even 100 years ago, the atom was considered the building block of reality. However, experiments and discoveries by people like Max Planck, Albert Einstein, Niels Bohr, and others showed that atoms are made of even smaller parts. The behavior of these tiny particles goes beyond classical physics, leading to the creation of modern physics. Modern physics explains the fundamental particles of the atom. Electrons, quarks, and neutrinos are the fundamental particles that make up all of reality. All matter in the universe is a mix of these fundamental particles. But the story doesn't end there. Quantum physics reveals that the fundamental building blocks of the universe go beyond particles. They are woven into the fabric of space and time. In this reality, the universe is not made of particles moving through space and time, but of regions of energy and gravitational fields sewn into the fabric of space and time. These quantum fields are recognized as the components of reality, forming the quantum world from which our reality emerges. It's a world full of wonders and strange phenomena. Now, let's enter that world. The universe and all celestial bodies are made of atoms, and atoms are made of protons and neutrons. These particles are not the smallest. According to the standard model of modern physics, there are even smaller particles. But before moving forward, let's take a look at the atom. In reality, all of physics can be described within an atom. On Earth, there are 90 elements and atomic compounds that nature has created. Each element has a nucleus at its center, made of protons and neutrons, surrounded by electrons equal in number to the protons. Each element has unique properties, like hardness, color, melting point, density, conductivity, and many other things. But the most important feature of an atom is the number of protons in its nucleus. In our real world, everything follows the law of cause and effect. Every specific action has a specific result. For example, if you poke a balloon with a needle, it will immediately burst, and there is no other outcome. However, in the quantum world, things are different. Nothing is certain, and no action has the same reaction every time. Probabilities are one of the main foundations of the quantum world. In this world, there are no definite systems. Everything is divided into groups of probabilities. If we measure, observe, or intervene with enough precision, we might see a specific result. However, these measurements, observations, and interventions themselves change the state of the quantum system. This behavior of the universe's components has been known as the mystery of quantum mechanics for years. In the quantum world, a particle does not stay in a fixed position. Instead, it exists in a superposition, meaning it can be in two or more places at once in a single timeline and have different properties. This phenomenon is impossible in our real world. For example, a person cannot be in two places at once in one timeline. But in the atomic world, this is possible. In 1935, Erwin Schrödinger conducted one of the most famous thought experiments in physics. Imagine a cat is trapped in a closed box. Inside this box, there is a vial of cyanide gas, a hammer, a radiation detector, and a radioactive source. Radioactive particles are emitted at random, and their behavior is described by a half-life. Suppose the detector and hammer are set up so that if a radioactive particle is detected between 12:00 and 12:01, the hammer will break the vial of gas, and the cat will die. If you open the box at 12:01, what will you see? Based on the half-life formula, you predict a 50% chance of radiation emission between 12:01 and 12:01. Thus, the cat has a 50% chance of being dead and a 50% chance of being alive when you open the box. However, when you do open the box, you will see either a dead cat or a live cat. You cannot say that 50% of the cat's cells are dead and 50% are alive. In an instant, probability turns into certainty. This thought experiment is one way to interpret the features of quantum mechanics. As mentioned, you can never measure the exact state of a system until an observer observes it. The Schrödinger's cat experiment indeed brought the quantum world into our understanding of reality, forcing us to accept its implications. Our grasp of reality is limited, and we only perceive a very small part of it. The principles and subfields that structure reality are largely hidden from our eyes. When we talk about particles, we're discussing tiny points in space filled by a mass. In reality, particles are forms of energy or vibrations in the quantum field. For instance, photons, which are particles of light, are oscillations in the electromagnetic field. These fields permeate the entire universe, meaning the essence of a photon exists throughout the fabric of space. In essence, light exists everywhere, and these are called virtual particles. They emerge everywhere, but disappear quickly, even where there isn't enough energy to create a particle. The quantum world also has a negative feature. A field is not directly observable. Why? Because every experiment requires energy, and that energy creates a particle in the quantum field, so it can be concluded that it is no longer a field but a particle, and each particle is in conflict with its own antiparticle but with a different charge. A particle can behave like a wave under special conditions. So even the meaning of a particle in the quantum world becomes a probability. If we attempt to determine the reality of a particle, we lose its rotational angle, and conversely, By measuring its rotational angle, we lose its position. This issue is Heisenberg's uncertainty principle, which states that even these parameters themselves are uncertain. Here, three properties define a quantum particle: mass, charge, and rotational angle. With these values, mathematical equations can describe a particle as a wave function, predicting its probabilistic behaviors. This implies that a particle, once observed, loses its quantum values and enters a fixed position. To change quantum values, we need more than just an observer's eye and a brain. Consciousness plays a role, but there are many theories ranging from mindful awareness to concepts involving the soul or being seen by an eye in parallel worlds, among many other ideas. There is no direct answer here, as the nature of quantum mechanics and its interaction with consciousness remains a topic of ongoing exploration and debate. Today, we've learned something, and the cosmos has shown us something. The laws of the cosmos are very strange but constant. They fundamentally differ from each other but converge somewhere. The reality of our world, what we see or hear, ultimately boils down to one thing: they are measurable. This is the distinction between reality and probability, and this inability to measure precisely is what has posed challenges in our understanding of quantum physics. These are profound questions that challenge our understanding of reality and the nature of the universe. Can we call this world and universe real if they have emerged from an invisible and probabilistic realm? Since this cosmos has arisen from a non-measurable world, can we consider it real? Are quantum waves meaningless? Do particles always deal with probabilities? And countless other questions for which no one has definitive answers.